The two courses are really diverging here. Dr. K is really getting into derivatives and improving derivatives of functions from interesting spaces, like functions of matrices and such. Dr. McCohen is going through kind of more standard stuff, like a very important implicit function theorem, and then some of the basic operations on vectors, especially in R3, these guys. So let me, I guess, do something interesting. Let's do this once I get my pen to work. So derivatives, and how to find derivatives of interesting functions. So well, this is not a very interesting function. Well, okay, but I could technically find the derivative by extracting the linear part. Of this expression, the difference, right, between the function at x and the function at x plus some. Okay, and we'll see why this kind of works nicely. So what happens is that the function at x, it cancels, and you're left with this expression, and we're looking for a linear operator on h. Okay, so we just want something times h, so this is 2x. So we can then speculate that the derivative of the function should be 2 times x, and it is, right? Okay. So a more interesting example would be if you have x is an element of n by n real matrices. So this is for Dr. K's class, really. So we'd say that's the something from the linear transformation from Rn into Rn. So that's like the set of n by n matrices with real number entries, say. So it's a matrix, n by n matrix. And so maybe you think of a function from this space where you square the matrix to get another matrix, right? So it's a function from this set of matrices into the set of matrices. So how can you compute a derivative? So let's make it cubed. Well, one way is to, if you look at the definition of derivative, right, you have the difference in the values of the function at x and x plus h minus the derivative of f at x, and that's going to be acting on h. It doesn't have to be just a pure multiplication, it could be something else. Okay, and you divide by the norm of h. So here it's the matrix norm, and you want that to go to 0 as the magnitude of h goes to 0. Okay, and then this would be called the derivative, right? It's a linear operator. It's linear. So a way to get a good candidate for this linear operator is actually focus on this expression and try to extract the linear part. So in our case, the function cubes the matrix. Okay. And so you can multiply this out. With matrices, of course, you have to be careful because x times h is not the same thing as h times x necessarily, so when we multiply this out, we don't have like terms necessarily. So you have h times x and then, oops, x times h. And h times h here. So you get x, so I'm just going to multiply this out. I'm just distributing the x into the parentheses. And then I'm going to distribute the h into the parentheses. Okay, and then we have that minus x squared. So I just kind of expanded that. It's a cube, by the way. So these cancel. And then you look for, in the remaining expression, you look for the linear, things that are linear on h. So essentially things that have just a single h in them, not h squared or two h's in them. So it's this business. Okay. The other parts are like non-linear in h, like that and that. You have the h's squared. That's nonlinear on h. Okay. So this suggests that a good candidate for this derivative of a matrix cubed at x acting on h. Oh, what am I doing? It's not a vector. Would be the linear part that he extracted. Let me actually write it a little differently. Let me write it as h times x squared. Where is it? Where is it? This, okay. Plus xh x plus, and where's the final one? X squared times h. Okay, so we're going to come back to this when we look at derivatives of multilinear maps, and we can find the same derivative. So that's a derivative of x cubed acting on h there. Now, the reason this works is if you go back to the definition, if I can get this to work, okay. So what would happen is that the x cubed would cancel out. We said the derivative is the linear part, right? So you're subtracting it from here so that the linear part goes away. And so if you simplify this, what's going to be left is just the nonlinear part, the stuff that I circled over here. Okay. So, yeah, so let me write that down. So after you do all the subtraction, you're just left with h squared x oops. So it's just again, just the nonlinear part would be left over after you do all the cancellations up here. Plus h cubed. Okay. And if you take the norm of this, so let me just take the norm, you can use the inequality for norms. the norm of matrix A times B is at most the norm of matrix A times the norm of matrix B. And you can also use a sort of triangle inequality, right? It's a norm, so it follows triangle inequality. So you get the norm of this is less than or equal to the norm of x. So notice that all the terms are going to have like an h to a power which is greater than 1, norm of h to a power. Okay, make that smaller maybe. Okay. So I'm kind of using a triangle inequality with, gosh. And you're dividing all this by, oops, the norm of h, I apologize. Yeah, my whiteboard's very laggy right now, so okay. So if you divide the norms, you divide norm of h squared divided by norm of h, you'd be left with terms, all of which have a norm of h in them. But we're going to let the norm of h, that's 3 of those. So you're going to have 3 of those, and then you're going to get a norm h squared. But that, of course, goes to 0 as the norm of h goes to 0. Okay, so that's I just wanted to people in Dr. K's class to know that there's a way of finding derivatives of these interesting functions, say on matrices, by simply looking at this thing, expanding the function if you can, and then a good candidate for the derivative would be the linear part on h. So only one h, right? Where's the end? Okay. Okay. Now, the way Dr. K presented this in class was to use a very nice general theorem for multilinear maps. So you have M is a multilinear map. M, say. So if you want to find the derivative of that multilinear map, and it acts on vectors, so like say x1 through xn. Okay, so we want to find the derivative of a multilinear map at these arguments at this point, acting on h's, right, was where you evaluate the multilinear map, and you replace the first argument with h1, but leave the other arguments alone, right? And plus, it's a summation, and then you would replace x2 with h2. Okay. And so on, right? Until you just kind of replace each x by the corresponding h one by one, take turns. You get hm. Okay. So this is very useful, for example. I mean, so if we look at the f cubed example, we can define a multilinear map on matrices of 3 matrices. Right. So matrices are vectors in a certain vector space. Okay. So, and you can, because matrix multiplication is linear, this is actually a multilinear map on matrices. Okay. So according to this derivative rule, this derivative of the function acting on h1, h2, and h3 So yeah, these are not just simple vectors, they're matrices. We would just, in the function, we replace x with h1, then we replace y with h2, and then z with h3. Okay. And apparently what the argument he made in the lecture is that if you then think, if you replace x, y, and z with just x, right? So you want to evaluate this derivative at x, if you will, acting on just a single h, say. This would be h x squared plus xhx plus x squared h. Okay, so that would be the derivative of x cubed. Okay, and that's exactly the same derivative we got when we extracted. If I may go back, it's exactly the same derivative we got by extracting the linear part from this. Okay. All right. So, any questions about that? Yeah, thank you for joining me today. All right. So another example of this idea is there's a function from Rn into Rn. So I'm going to be happy that he's changing it so I could just do this problem. And it's defined as x crossed with x. And he wanted you to find the derivative of this function. We know that that's going to be a n by n matrix. Yeah. So there's a couple ways to do this. You can just, of course, do the kind of, well, it's not Rn to Rn, I'm lying. Let's say it's either R3 to R3 or R7 to R7. So apologies. Cross product, right? We do that in R3. Okay. So it's a 3 by 3 matrix. Okay, so how can we find the derivative without going into expanding the cross product and taking partial derivatives to get this 3 by 3 matrix of partial derivatives? Well, you can use either the extract the linear part from here, okay, so if we do this, this is going to be x plus h cross product with itself minus x cross x. Now this is really, do you see why he's changing this problem, by the way? Does anybody see why he would? Does anybody see what the, can anybody tell me what the derivative has to be? Yeah, exactly. The cross product of a vector with itself is a zero vector. So this is like a constant mapping, constant function, always returns the zero vector. So this 3 by 3, so the derivative has to be the matrix of zeros, right? It's a constant function. Okay, but we'll see that. So cross product is multilinear, so you're going to get x cross x plus x cross h plus h cross x plus h cross h minus x cross x, right? Now, besides those being zero, you can say they cancel. H cross H is 0, and then remember that cross product is antisymmetric, so H cross X is the negative of X cross H, so you get 0. So you can think of that as the linear part acting on vector H. So it's like a matrix multiplying vector H. Yeah. And it also works in the definition, but he's changing that problem. And the other way, of course, is to think of since cross product is multilinear, think of the function on two vectors, which is their cross product. And according to the formula for the derivative of a multilinear map, we can differentiate, we can evaluate, we need to write that this is acting on two vectors, H, say, and K. Yeah. So this would be the map where you place the first argument with H, then plus the same map where you place the second argument with K. So this is H cross Y plus X cross K. So that would be the derivative for the function. But if you replace the argument I think he was trying to make in class, this would give you H cross X, and then X cross H, and since the cross product is antisymmetric, this would be 0. Yeah. The 0 vector. So you think of it as the 0 matrix multiplying the vector H. Okay. Anyway, so I think that's enough about derivatives from Dr. K's class. Are the rest of you in Dr. M's class? Yep. Okay, so let me. If somebody wants help with like product rule or the quotient rule problem on homework 5 in Dr. K's class, maybe you want to come by the tutoring lab. Okay. So let's move on to Dr. M's class. So how do you feel about implicit function theorem? Very important theorem. So. Okay, I see you're very excited about it. So let's look at implicit function theorem. And let's do a simple example where we have, let's just say, okay. Let's say that's equal to 4. So what's the natural? Well, not the natural. So this is some function on R2, and we're setting it equal to a constant. So the graph of this is the level set of f. Okay, and we want to know whether we can think of this level set of f in a way where, let's say, we can we think of one of the variables. So can we think of y, let's say, as a function of the other variables or variable x, so g of x. So can we think of y as a function of x? And furthermore, can we think of it as a C1 map? So it's differentiable and those derivatives are continuous. So that's the question. And that's going to be always a local thing, so near a point. So near the point, say 1, 1, right? So x is 1, y is 1. So near that point, if we look at that level set, can we think of y as a function of x? A continuous, a differentiable function of x? Well, to answer the question, you might just assume yes. Right? And then you say, well, I want to then differentiate. So if the answer is yes, y can be thought of as a function of x, then we can implicitly differentiate to find dy dx at the point 1, 1. Right? So we just differentiate both sides with respect to x. So x would be, we're treating x as the independent variable, and we're treating y as this function of x. So implicit differentiation, right? So we just differentiate both sides with respect to x. Remembering that y is a function of x, so I need to use product rule here on the first term, right? So that's the product rule in the first term. And then plus, and the product rule in the second term. Okay, so first term, second term. Third term, derivative with respect to x. And then the fourth term, so derivative of y cubed, and then y is a function of x, so chain rule. And on the right-hand side, we get 0. Okay. So next, I'm just going to rearrange. So I'm going to collect all the terms that don't have a dy dx as a factor. Okay. And then gather all the terms that do have a dy dx as a factor. Okay. And so now we can, so what I want you to notice is, if this is my original function, the important thing I want you to notice is that if we were treating x and y as dependent variables, this over here would be exactly, let me move this. Okay, this part would be exactly the partial derivative of f with respect to x. You can confirm that if you differentiate your function with respect to x, treating x and y as independent variables, did I miss something? So you get 2xy. Oh, yeah, my bad. Okay, there you go. It's fixed. So if I differentiate this with respect to x, I would get that term at xy. Plus, and this part is the derivative of f, but with respect to y, if we're treating x and y as independent variables. And then times dy dx, which came from treating y as a function of x, so chain rule. So the question is, can we solve for dy dx? Under what circumstances can we solve for dy dx? Oof. Oof, differential equations. Oh, right. True, yeah, find the solution, right? Well, there you go, equal to C. Okay. Um, um, so we can solve for dy dx if this part here, this derivative of f with respect to y, is non-zero, because then you can just you can just bring this term over to the right, so you get negative derivative of f with respect to x. And you can divide by this if it's non-zero. Okay, so you could do this if so the derivative of f with respect to y at the specific point cannot be zero. Okay, and if you can solve for the derivative of y with respect to x, right? Then you have a good linear approximation to this function, and you can assume that indeed y can be considered as a function of x near that point. Okay. In our case, it was 1, 1. So we would get, just to complete the process, dy dx, this at 1 is equal to 6, and this at 1 is equal to 6. So our derivative is negative 1. And that's at least a starting point for trying to find something about the function, right? Like what it is. Okay, so here we took partial derivatives with respect to x and y, and then because we were thinking of y as a function of x, we had to use chain rule, and since this function was equal to a constant, we got 0 on the right hand side, and we were only able to solve for the derivative if this was non-zero. So the more general implicit function theorem does exactly this chain rule procedure. So I'll give you the formula now. Okay. So imagine we have a function from Rn plus m into Rm. Okay. And so think of x as being a vector that's in Rn, and y as being a vector that's in Rm. And what we have is a level set of this function. So let's equal some constant vector. So this is a m by 1 vector, right? Because the output has m components. So this is a constant vector. And we want to know whether we can we think of this y as some unknown function of x near a point, right? Where this corresponds to a specific x vector, and this corresponds to a specific y vector. Okay. Now, so if we assume that we can, let's see what would happen. You have the function of x and y is equal to some constant. Okay, where we're thinking of y as a function of x. So if you were to differentiate both sides, okay, on the right-hand side, of course, you would get 0 because the derivative of a constant vector. It's a 0 matrix, by the way, because. So let me just make sure it's 0 matrix. Okay, but on the left-hand side, you would use a combination of, well, you would use chain rule, right? So what we can do is, let's write this as, we can differentiate the function with respect to x. So just the x's. And then times the derivative of x with respect to x is just the identity. Plus, you can then differentiate the function with respect to y. But then when you use the chain rule, you're going to get the derivative of y with respect to x. So you're going to get the derivative of g. And that's equal to the zero matrix. Okay. And then you would evaluate this specifically at the point AB, right? And then you can solve for the derivative of this function at A using linear algebra. So you would bring this this factor over to the right, making it negative. And then multiply by the, so, okay. So f has n components and x has n components. So this is going to be an m by n matrix. Here we have my components and the function has m components. So this is an m by m matrix. And this derivative, so if you look at this function, G takes vectors from some subset of Rn and maps them into Rm, right? Because y has m components, x has n components. So the derivative of G will be an m by n matrix. Okay, so the dimensions here agree. But the key here is that this is a square matrix. Okay, and if it's invertible, we can just multiply both sides by the inverse. And I will do an example where hopefully this will be clear. But I'm just giving you a formulaic way. Okay. So, but this whole solving for the derivative of G at A depended on this matrix being invertible. Okay. And if it is, then since we can solve for the derivative of G at A, then means the function can be approximated, right? So it exists. So the derivative, so to make this formula nice, okay. Again, you differentiate your function with respect to just the y variables evaluated. And if that's invertible, then we know that y can be thought of a function of g, a C1 function, in fact. So if the derivative of your function with respect to the y coordinates is invertible, so the determinant is non-zero, then there exists a function g where y can be is a function of x, not C1. Okay, so I know that was a lot, so what I'm going to do is just do an example. Okay. 1, 1. All right. So let us do an example. And I'll just use the, well, okay. So suppose we have x, then y cubed, y1 cubed. What point did I choose? Oh, geez, what did I write at the point? Well, that sucks. Y1 was 2. No, but I can. Next time, just record what I write. I would have to do it in OneNote, but I could do that. But that would be next time. Oh, there we go. So we have a function. So we think of a function on x, y1 and y2, and it's defined by these two components. Okay. And we're looking at a level set for this function. So it's all the points that map to the constant vector -4, 2. So it's a level set of f. Okay. And we want to know that if we look at this graph, let's say near the point 1, -2, 1. Sorry. I don't know what this is supposed to be. What did I write? Okay. Sorry, that was 1, -1, 2, 1. Okay, thank you. All right. So near this point, can we think? Is there a C1 function where we can think of two of the variables, well, let's say the y's, as a function of x? Okay. Near the specific point. Okay. Well, so we said that, okay, I'm going to compute the derivative of f at this specific point. But I'm going to differentiate just with respect to x, just the x, right? So that'd be, so you differentiate the first component with respect to x. And we're treating everything as independent variables here, so okay. And then you differentiate the second component with respect to x. Okay. So that's a 2-by-1 matrix. And then we're going to evaluate this at the specific point. Okay. So we're next take the same function but differentiate just with respect to y. The y coordinates, right? So you take the first component and differentiate with respect to y1. And then differentiate with respect, the first component with respect to y2, just the standard matrix of partial derivatives. And then you take the second component and differentiate with respect to y1. There's no y1s there, so that's 0. And then differentiate with respect to y2. These are partial derivatives. Okay. Right, so that is indeed a square matrix as advertised, 2-by-2. And we're going to evaluate this specifically at the point So let's see what we get. For -6. Wait a minute. No. All right, so 3 times -1 times y1 squared. Okay, so that's -12, and y2 squared is 1. So, well, I guess that's right. -3, 4, -12, plus 1. This would be 1 over y2 squared. And this would be 4. Okay, so then we said that when we use the chain rule, right, when we said, okay, let's think of y as a function of x, we had the derivative of f just with respect to x at the point, plus the derivative of f but with just respect to y at the point, and the chain rule gave us the derivative of g at a, and that was equal to the 0 matrix. And we said that if this matrix is invertible, so we check the determinant, and that's equal to 11/4, sorry. So that's not 0. So we know that this matrix is invertible, and now we can solve in this equation for the derivative of g at a, so at x equals 1. And that would be, bring this to the right-hand side, so minus the derivative of f with respect to x, really laggy. Where was it? 8 -1. And then we would multiply by the inverse of this matrix, so 1, so the inverse of that matrix. Yeah, that was the formula. And so quickly computing the inverse. Okay, and what do we get? So now notice that g was a function from r to r2. Okay, because we had y1 and y2 are some function of a single input x. So this derivative at a is going to be a 2/1 matrix. So it's going to be the partial derivative of y1 with respect to x and the partial derivative of y2 with respect to x. Okay. So at 1, or at 1, you would get that this is -8/11, and this is -44 over 121. But, right, so the implicit function theorem allowed us to say that yes, y is some function of x near the point. And furthermore, it's a C1 function. And furthermore, we have a formula for the derivative of this function at x, so at a, at -1. Well, whatever. That was -1. Okay. All right. Do you want to do another one, or do you want to? Let's see. Can you think you can? Right. What? Oh. Oh. Okay. Thank you. Okay. Now, we didn't have to be. I mean, you could do this. X1, X3. Okay. You could be. Let's make this simpler. So. Let's see if this works. 1, 0, 2. I don't know what the previous answer. I don't. The numbers don't matter so much. It's a procedure. Okay, so can we think of? So you have. So can we think of y as a function of x and z? So is there a C1 function where y is a function of the other variables x and z? Now, we didn't have to use this kind of high-powered matrix algebra business, because we can just say, well, what would be the sufficient condition? If y were such a function, then we can differentiate y with respect to x and then with respect to y, if there were such a function, right? So let's do that. Let's differentiate this with respect to x, where x and z are considered the independent variables, and y is dependent because it's a function because y is a function of x and z. So when you implicitly differentiate with respect to x and then y, you have to remember that, you know, which variables are independent and which variables are function. So we're going to differentiate this with respect to x. On both sides, obviously. And so we're going to use product rule. Because y is a function of x, right? And here, we don't have to use product rule because x and z are both independent variables, so that you just get z. Okay. And then do the same thing to both sides of the equation, but this time we're going to differentiate with respect to, z, the other independent variable. Okay, so differentiate with respect to z. Again, remember that y is a function of z, so you have to chain rule that. And then x. Okay, so you get these two equations. And then you can solve for dy dx. So we think of it as, say, it's a system. So you can think of it as y squared plus z x. You can just use linear algebra to solve this, right? And that's equal to 0, 0. Okay. So I picked the wrong y value. Okay. So z would be 0. That's fine. Okay. All right. So now it's obvious that this derivative would exist if this is invertible, yeah, if it's not 0. Okay, so that way we can bring this vector to the right-hand side to make it negative, and then divide by 2xy, as long as x times y is not 0. Okay, but we're doing this specifically at a point, right, 2, 1, 0. So we'd get the derivative of this unknown function when x and z are 2 and 0 is 1 over 4. That's 4. And then here we get y squared plus z, so 1, then x. Okay, but as long as this is invertible, right, it's not 0, then yes, y can be thought of as a C1 function of x and z. And in fact, we have a nice derivative of it, right? Again, notice that this was, if our function was, let me just write it this way. X times y squared plus xz. Then this was exactly the derivative of this function with respect to just the independent variables, right, y and z. Right, if you differentiate this with respect to x, you get that. And if you differentiate the same function with respect to z, you would get this x. Then plus, and this was the derivative of the same function with respect to y, 2xy if you differentiate. So, all right. It's actually a nice and tidy formula. I already wrote it. Okay. So any questions about implicit function theorem? All right, what else do we need to discuss? I believe you went over like gradient, divergence, curl. So let's try to organize all that. Okay, so let's look at, make the distinction between a vector field, say on R3 or Rn. So this is a function, let's use capital F, which maps, which puts a vector for each point in space, an n-dimensional vector. So for example, right, you have 3 inputs, and this would give you a vector. So it's a rule that assigns a vector in each point in space. that's a vector field, as opposed to a real valued function, which sometimes is called a scalar field. Like, so this is like more like physics talk, right? So f would be a function for each point in space, we assign a number. So this is like wind velocity on a weather map. This is like temperature on a weather map. Okay, so we'll use lowercase letters for that. All right. So especially in R3, because we're going to be talking about the curl, so I guess we're going to restrict our attention to R3. There's standard operations on these vectors and scalar fields. So operation, I should say, spelled correctly. And then we'll have what the input is. So what are you operating on, and what kind of object do you get out? And then we'll look at the notation using the Dell operator, or maybe triangle. Okay. So the first kind of operation is the divergence of divergence. And we always take divergence of scalar fields. This is a scalar field. And what comes out is a vector field, so big F. And the notation would be del of a scalar field gives you the corresponding vector field. Right. I'm going to try to complete this table, but maybe I'll just make sure that here's a scalar field on R3. And this is the gradient as you know it. So, right. So the gradient of this function, you're well and familiar with this, is just the matrix of partial derivatives. So yes, this function assigns a number according to this rule to each point in x, y, z space. And when we take the gradient, we get a vector field. So it's like a new function that assigns a vector for each point in space. So it's just your matrix of partial derivatives with respect to x, y, and z. Okay, it's an example of that. All right, so then what else? Well, what if we have, for the input, we have some vector field? And for the output, we're going to have a scalar field. Should have used maybe. Okay. So what kind of operation are you familiar with, or you've heard about in class, which takes a vector field, does something derivative-like to it, and out of it you get a scalar field? Oh my gosh. Completely brain fart. Yeah, thank you. Gradient. The gradient of scalar field is a vector field. Yeah, divergence. Right, and as you can see, the del notation is that you take del dot f, the vector field, and so that's it helps you remember how to compute a divergence of a vector field, and also tells you that the dot product of vectors is a scalar, so it helps remind you that you get a scalar field out of it. So for example, if your vector field is this business, okay, and then so the Dell operator you think of as an operator with the derivatives with respect to the spatial coordinates, right? And so del dot f is supposed to remind you that you're just differentiating each of these components of the vector field with respect to the the x, y, and z respectively, right? So you get derivative of this with respect to x, derivative of this with respect to y, and the derivative of this with respect to z. Okay. So indeed, you get a new function which, for each point in space with x, y, z coordinates, right, assigns a number according to this rule. So I get a scalar field. Okay, so what other combinations have we left out here of inputs and outputs when we're just thinking about vector fields and scalar fields? Vector field and vector field. So what kind of operation do you know which takes a vector field, does something derivative-like to it, and outputs a new vector field, so uppercase G. Curl, yeah, very good. So that's the curl of the vector field. Gives you another vector field then. Again, the notation using the Dell operator is del cross F gives you a new vector field G. Okay, and again, so if you, the Dell operator is like a vector of derivative operators. This is a vector field, and when you take the cross product of two vectors, you get another vector. So that's supposed to not only help you give you computational way, remind you how to compute the curl of a vector field, and this is on R3. By the way, this vector field has to be on R3. Okay, and then finally we have the Laplacian. So so that would correspond to the only kind of other combination of inputs and outputs when we're considering just vector fields and scalar fields. Sorry, this whiteboard is so laggy. Okay. So you have a scalar field, and the output is another scalar field. And so this is the, so it's actually a composition of the previous operations. So like you can start with a scalar field over here. You can take the gradient of it, and the gradient then results in a vector field, right? But you can take that vector field in turn and find the divergence of it, right? Which would then yield a scalar field. So we can define the Laplacian to be the gradient, but you can take the gradient of a scalar field to get a vector field, and in turn you take the divergence to get another. Okay, so this can be thought of as, sometimes this is written as del squared on F. You might even see triangle or something like that. But at least to me, this is just more consistent with, it tells me what to do. And it's just gonna, if you think about this, it's gonna amount to the partial derivatives, the second order partial derivatives of F. With respect to the variables. Let's say for an R3, we have a scalar field defined on R3, right? And this would give you a new function, new scalar field. Okay. So that's a kind of summary of this typical kind of derivative-like operations on vector fields and scalar fields, at least in R3, so important to physics. We can prove that, for example, so do you remember do you know how to check whether a vector field is conservative, like what that means? So this should be if you're in differential equations, right, this should be like, I have nightmares. Okay. So here we can say that a vector field is conservative if it comes from being the gradient of some scalar field, j sub x I sub y. J sub x equals I sub y. Oh, okay. I know what you're. Yeah. I know what you're saying. Right, but more generally, so like you say, suppose you're not just in 2 dimensions, right? So your vector field could be defined on Rn, or maybe you're in 3 dimensions or 4 dimensions. The more general way is to say, well, if my vector field is born out of being the gradient of a scalar field, we would say that vector field is conservative, in the sense that line integrals, work integrals for that vector field are 0. Are independent of path. But this is a test, so this is the definition, say, of conservative. In physics, there's a little change, like in physics, let's suppose you have an electric potential. What time is it anyway? Okay, electric potential. Then you'd say that the electric field is the negative of the gradient of that potential. So a little switch, you have to do physics stuff. But mathematically, essentially, we're just taking the gradient of a scalar field to get a conservative vector field. And how do we test that the scalar field is, let's say we have if you have a vector field on R3, how can we test? Well, if we take the curl of a vector field, right, and it gives you the 0 vector everywhere, right, on some domain, then this means that f must have been born out of taking the gradient of the scalar field, because we can prove in general that as long as G is sufficiently smooth, so G has to be C2 to use Clause's theorem, mixed partials being equal, then we can prove this identity. The curl of a gradient of scalar field, assuming your scalar field is sufficiently smooth, will be the 0 vector, right? And so we have hope that so this is kind of like in differential equations, we would say that this is exact, right? Okay. So if the curl of your vector field is 0, in some domain, then we can hope that we can recover some scalar field that's equal to the vector, whose gradient is the vector field. So this is the test for conservative vector field. And then maybe part of the work problem would be to actually find a scalar field whose gradient is the given vector field. So do you have any questions? Because I think I need to end it here, but I'm happy to answer questions.